calls, how the address in the target code will work for procedures. So before we move with the discussion, we will start with a fact which is known to us. See, this figure I remember still now, it was given by my teacher when he discussed about interrupts in the CPU class. So remember that, Mr. Mujibur Rahman. He drew this diagram to give us the concept of interrupts. And the same diagram I repeat now. See, this is the main program. This is the main program, and this is our function call. So main program continues at this point. From here, it is calling. Main program is calling a function. What happens? There is a branching to this instruction. Then the function body will be executed. There will be a return statement, and where it is returned to the place. See, here we have an address, and immediately after that we have an address here. If this address is 100, suppose that this is 1008. So from 1000, then next instruction is 1008. But before doing that, function call should be completed. After that, 1008 is to be resumed. This is very easy to say, and this should be done by the program whenever a function call is being done. So what are the extra arrangements required by the compiler to simulate this action? Here, in compiler, for every procedure or function call, a separate data structure called activation record will be kept. We don't have a specific discussion about activation records in our syllabus now. It was there in the earlier syllabus for Aisha Harris. Now, in the revised syllabus, this part of the module is not explicitly present. Still, we have to understand that every function call will be represented as an activation record, which is called as AR in short. So I may even refer to AR. Don't confuse what's AR. Activation record is a special data structure kept by the compiler whenever a function is getting invoked. It has a lot of fields. Activation record. One important field is that when a function is getting called, of course, program counter will be loaded with the first address of the function body. We know that. After the return statement, then the remaining part of the main program is to be executed. So we can see that at this point, our program counter is getting loaded with a new value. After this function is getting executed, the address to go is to be explicitly specified. Otherwise, program will not, the system will not know from where to resume. I got you got the point. When we have a return statement, it is an indication that function call is getting over. Once the function call is getting over, the place from where the deviation had come, next to that place, the instruction is to be resumed. That means address of at this point is to be stored somewhere, and it is to be given back to the program counter. So suppose that when a function this function is getting called, before going to execute this function itself, system will have to store the return address. So return address will be kept in the initial part of the activation record for this function. Suppose that main program calls a fact subroutine. Main program will be having an AR, activation record. Fact will be having one more AR, activation record. So we have two records now. In the activation record for this fact, return address to be moved after executing main will be stored. That's arrangement. So before jumping itself, the place to return is also getting stored by the system. This is arrangement. So here, what will happen? As and when fact is called, the return address in this place, this is the return address. This address will be kept in the activation record of function call. As soon as the return statement is encountered, main program will refer to the activation record of the fact function. It will retrieve the return address stored there, and that will be loaded to the program counter. Hence, the program will resume as if nothing had happened. So this sequence of events we have learned. We have I will underline that we have repeatedly learned. We have learned about this in UG days when in our first C programming class. Then whenever we use functions, we repeated this. When we discussed about interrupts in the machine organization class, then also we have repeated this. And this fact we just retrieve now for the remaining portions of the class now. How to implement machine codes for function calls. See, these are the three address statements that represents simplified procedure calls. An action is a place where other three address statements that could be instructions within these functions or after the call instruction. It will be specified as action 1, action 2, like that. So they are actually labels of codes. Caller and callee, we know about this. When a function calls another function, when main program calls a factorial function, fact is the callee and main is the caller. So both has to be represented and recognized. First case is static allocation. So how the code in the target code is generated. Here we have to worry about addresses. And we also mentioned in the last class that there will be a special data structure called as activation record whenever a function is invoked. The time of invoking a function, system will generate an activation record. Designer will have to make provisions for this. Each function call will be having its own activation record. Suppose that we have a recursive function call. As and when the function call is being made recursively, corresponding to each recursive call, a separate activation record will be maintained. Now, size and layout of activation records, it will depend upon the details stored at a symbol table. Exact layout will vary from compiler to compiler, but there are some common activation fields in the activation record. And one item is the return address to which the main program is to be resumed. So let us see how in static allocation, what do you mean by static? Static means the address is known at the time of compilation. Dynamic means when we do the compilation, address is not known. That is the variation, static and dynamic. So if we know, suppose that int I equal to 0, there The question of allocating a memory location to I is simple, because at the time of compilation, compiler will know that I is an integer variable and it requires this many bytes. So it can be allocated an address. That will be static allocation. But dynamic allocation will be done at the runtime. Even for this, compiler will have to make arrangements. Now a call-callee statement, that means here a call-callee will be in our high-level program, it will be just fact. We are calling fact from the main program. And that will be represented as call-callee or call fact in the intermediate code. Now, what should be done? Here we know that whenever a main function calls a subroutine, execution of the main program will be temporarily kept away. Program counter will be loaded with the starting address of the callee. And that's what is being done here. See, callee, and before, and we also told that, and that is what it's done in the second statement. See, br callee code area. The first statement will store the place to return after the execution of callee. So initially, now you just note down these two statements. Whenever there is a function call, that function call will be implemented in target code as a sequence of these two statements. When call fact, suppose that you write an intermediate code and you have represented a function call like that, call fact. Now fact is to be executed. That is meant by call fact. So each call statement, each invocation to a function, whenever we make a function call, that is represented by these two statements. One is a store instruction and the other is a branch instruction. Then now we look at these two. What is the purpose of the store instruction and what is the purpose of this branch instruction? We have seen that when a function call is being made, function is to be executed now. Main program was getting executed. So temporarily, now the focus will be shifted to the function body. After the return statement is executed, program counter should resume with the next instruction in the main function to execute further. That means the place to return is to be well known, and that is ensured by this first store statement. Before jumping, the place to return is stored. Then a jump is made to the callee's code area. See, ST instruction saves the return address at the beginning of the activation record. See here, don't forget about activation records for every function. Callee is here the function that is being called. So in the callee's activation record, beginning return address is kept in the beginning of the AR. What about these attributes? ST is having a callee static area. What do you mean by callee static area? This is a constant, and this indicates the starting address of the AR for callee.static area. And callee.code area is also an address. It points to, or it refers to, the first instruction of the code, actual code for the function that is being called. So here BR is followed by a constant. That means that address will be, branching will be done to that address. BR followed by a label. Here we are, we are storing we will store an address to this this area, this location. Now, what about hash here plus 20? So this value is to be loaded here. We have to compute this value, and this value should be stored on the activation record for calling. Now operand hash here plus 20. Entire store instruction will store the return address. Now what is this hash here plus 20? It is the address of the instruction following this BR. See, after BR, in front of above ST, it is the main program. Main program reached till here. From here, we are calling fact. Fact is getting translated as these two machine code instructions. So these two represents fact, call to fact. After the fact function is over, instruction that is at this location, that comes immediately after BR will be loaded. And that is what is getting stored here, return address. So hash here plus 20 will point to the location after the BR instruction. So here we have three constants and these two instructions. Their lengths, if we compute, we'll see that from the current place, we have to move 20 bytes. Now there is a halt instruction. Halt instruction returns controls the operating system. So main program, when the main program, what is an operating system? Operating system is a program that temporarily relinquishes its control to any program, and once the program is successfully or forcefully over, it will regain the control. This is one of the definitions that we have learned in our operating system class. And here halt will do just that. Whenever halt is given in a program, it is to return the control to the operating system. Now there will be a return statement. Whenever the return statement occurs, there is a change of instruction in the program counter. What is the return statement? Whenever a function call is being made, function will be executed. Last statement in the function body will be a return statement. And this return statement is translated or implemented using a BR statement. BR star call is static area. What is a static area? Static area is the beginning address of the activation record for callee. So before returning callee's activation record we referred, its first field will be for the return address, and a branch will be done to that address so that safely the remaining portions of main program will be executed. We'll see an example for this. Here we have C and P. C and P. C calls P. You can see it here. C calls P. So we have function C and code for C and code for P are given. See, these are placeholders. It represents some piece of code. So before calling P, there could be some code. And after calling P, there could be some code. It's natural. Similarly, code P will be having some source code. It is written as action 3. So action 3 is just a placeholder to say that there are some source code in these places. Our worry is just now only one thing: how a call P is to be implemented and how this return statement will be implemented. So we assume that the entire code starts at address 100. So this is the code for C. You can see. First part, the code for C is given. C is our main program. So at the end, we have a halt instruction. In the main function, we have a halt instruction, whereas in the subroutine, we have a return statement. So 100, see here, it is followed by this 100 to 160 is code for C, and we have this code for B here, code for B, and we have these instructions. Now let us see how this is getting implemented and how this translation is being done. Code for C, it starts at location 100. Now we have a call to P. When a call is being made to a function that is implemented using these two machine instructions, first the return address is to be stored, then a branch is to be occurred to the place where the called function's source code is being kept. So ST 364 140. Now this we have to explain. Before that, we assume that activation records for C and P are to be stored. And we discuss about static allocation. In static allocation, the requirement is that the place for ARs for C and P should be known in advance. So we assume that it is kept in 300 and 364 locations. The AR for C is kept at 300 and AR for P is kept at location 364, and that's what, and that is known in advance. Otherwise, static allocation cannot be done. Now, see action 1 call P and action 2 halt. This should be implemented first. So this is being done at instruction number 100. As we have seen, call P is now implemented as two instructions. A store instruction followed by a BR, branch instruction. Now, what is being done in this in this instruction? Hash 140 is given. Hash 140 is an immediate value. The value as such will be stored. What is this 140? 140, see, after calling P, control will be transferred to P, and once a return statement occurs, this is the place to be resumed, action 2. So we have seen that action 2 begins at address 140. So 140 is to be saved now. Return address is 140. It is being saved in 364. Why 364? Because 364 is the activation record for code P. Activation record for P, it begins at 364. So at the beginning itself, the return address will be kept. Once the return address in the main program is kept in the callee's activation record, then a branch to call P. Then now the execution for P should begin. Execution for P should begin at action 3. Action 3 is kept at address 200. So BR 200. So the control will be transferred to this place. Now code for P will be executed. Once the code for P is executed, it should return now. Return address, BR. Return is implemented as a single instruction. Each call will be implemented as 2 instructions, whereas a return will be implemented by just 1 instruction. We will simply branch to displays action 2. See, action 2 is stored at 140. Instead of calling 140 as such, we now know the place where 140 is getting stored. It is on the beginning place of this activation record for P, and there we have initially stored 140. So we can just say star 64. When we say star 364, value stored at address 364 will be taken up, and that location execution will be branched. So this is how in static allocation target code is implemented for procedure calls and returns. So you may be given an example and how to explain this, or you may be asked to illustrate these steps, how it is being done, or simply the basics, the fundamental steps. And so all these portions we should be able to explain how things are working, how a call statement is getting translated, how a return statement is getting translated, and if these two are clear, we can even frame our own example also. A simple exercise. See, the other statements we need not worry. We have to take care about only about call and the associated return. Other things it will be there. It should work as usual.